Hi there, welcome back to the formulaic approach. Now in today's video, we are going to be treating work, energy and power. Now trust me when I say that work, energy and power is the simplest topic in physics. It's simpler than remembering your name. No, it's simpler than opening your mouth when you want to eat. Yes, it's simpler than that. Alright, so the truth is that it's very simple, and it's especially because both work, energy, and power, all these three quantities are scalars. So because of that, when we refer to them, and no matter how they give you the question, scalar is very simple. Just know that it's very simple. All right. Now let's start or begin with work. So what is work? So you can easily, as a layman, you can define work as basically what you need energy to overcome, right? What you need some energy to overcome. So, but in physics, we define work. How do you know work has been done? We define work as the force acting on the body and the displacement that body, the force acting on the body times the displacement that force causes on the body. So, for example, if I have this chair on the floor, this chair, and I apply force and it moves, I know that work has been done on this body. Is that okay? So, principally in physics, we define work. It is denoted by W, take note of that. We define work as the product of the force acting on the body times the displacement it produces on that body times the displacement. So now it is easily described when the body were just, if the body were just on the horizontal ground and the force acting on it is maybe just in this direction, coming from this direction. So this guy is trying to push this guy. So maybe he holds this place. Okay, maybe there is an anchor or something that he holds and he tries to push. Okay, he's trying to push. So the work on this body will be the force that is applied by this guy times the displacement. Let's say this guy moved from here to this point, right? He moved to this point. So we'll say that this distance, let's call it or displacement x because the direction is definite. This displacement is known. So the work done by this body will be the product of the force that he applied times the displacement over which the body was translated. Now, but what if it's quite oblique? The position of the force that is acting on it is oblique. What will happen is this. So, for example, I have the same body on the ground, but this time the force that is acting on it, let's say this guy is very tall, for example, let's say this guy is very tall and he wants to push this guy, he applies force in this direction like this. Okay, so his hand is pushing in this direction. So let's just show one hand, or the two hands like this. So he's pushing like this, and something like this. How do you push? I guess it's something like this. Okay, so the guy is very tall, and he's pushing on this body like this at an angle. So the way we draw the free body of this thing will look like this. We look like this. The force is acting at this angle and the body is here like this. So in the free body, we will show that an angle is acting at the center of gravity like this. You see how we moved this force to the center of gravity because the highest mass of this body is concentrated, the mass of this body is concentrated at the center of gravity. So this point, because it's a regular object, the point at the center there is the center of gravity. So this guy is acting at an angle theta to the horizontal. Is it clear? So at an angle theta, let's put this as theta. Do you see that now? So because the force is now oblique, okay, the formula changes, okay? The formula changes. So with an oblique force, we need components, right? We now need to analyze components. We need the y component of the force. There are two components of the force, the f sub y and f sub x. Now, if you have not seen my video on vectors, you should do well to subscribe to the channel and check out the video. Now, because this is actually the origin of dot product of a vector. So now, looking at this, the force, is acting in between f sub x and f sub y components. Now, if this body actually translates in this direction, okay, so which component of the force we want? Is it the f sub x component that won or f sub y component? It is the f sub x component that won because this body is translating in this direction. So if that body moved into the direction, then we know that the component that won is fx. So by the time we bring out the vector, it looks like this. I mean, I will draw the vector because it's force, right? Here we have fx, fy is here. And here we have f sub x, but it's f sub x that won because this is theta and this is the f. This is where we are applying our force at this angle. Now, so it means that it's the fx that won, so we have to do the relationship between the f and the f sub x. F sub x is adjacent relative to this guy, and this guy is hypotenuse. So what trig function do you use for adjacent and hypotenuse? That is cosine theta. So cosine of theta will be what? Adjacent, which is f sub x over hypotenuse, which is what? F. So by so doing, we're able to find that f sub x, which is the component that has actually caused motion or resulted in motion, is going to be f, the actual f applied, times cosine of theta. So the actual force that is acting in this body, that the body will be feeling, is f cos theta. So in which case, if the body translated x displacement, then the work done by that force is going to be f cos theta dot times d. Is that clear? So the way we write it is work done equals f d cosine theta. Alright, so this is the origin of dot product. If you remember well, we said dot product is going to be equal to A dot B is equal to what? Magnitude of A dot magnitude of B cos theta. So, and that is the way it is there. Okay, so that's that for work done on a body. Now, let's solve some questions. Let's solve some questions. All right, so let us solve the following questions. There are 3 questions I've written here. It says, okay, so another thing that, after writing the question, another thing I noticed is we can also express this formula as W equal to what is formula for force, that is mass times acceleration there, then times distance. So in a case where the angle between them is 1, so the angle between them is 0 rather, so cos 0 is 1, okay, so that work done is mad. Or in which case, if it's an oblique force, we have MA d cos theta, of course. So where we know that MA blah 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 is that. So these are the different changes that could occur with the formula. So that's the number 1 question. Number 1 question says that a force of 500 Newton is applied on a body at an angle 60 degrees. So the force is 500 Newton. F is 500 Newton. Is applied on a body at an angle theta. So theta, angle 60 degrees. To the horizontal, calculate the work done by the force. This one is very, very simple. It's just like what I showed you here, yeah? So the distance moved, a force of that is applied at an angle 60 degrees to the horizontal. Calculate the work done by the force. Oh, sorry. The question is incomplete. I think I missed out the distance. Let me check again, please. Okay, so I'm very sorry. It says if it moves a distance of 8 meters, if it covers a distance of 8 meters, so I missed that out. I'm very sorry. So the distance is 8 meters. So our work done therefore becomes force times distance times theta. Okay, times cos theta, sorry. Okay, so W therefore becomes force, which is 500, multiplied by 8, then cos 60 degrees. So what is cos 60 degrees? That is sine 30, which is half, times 8, times 500. Here 4, so W Therefore becomes 4 times this, 20, 0, 0. So joules, sorry. The unit of work done, I didn't say, is also joules, okay? Unit of work done and energy is joules. It's named after James Prescott. James Prescott Joules. Okay, the guy was my friend, in secondary school. I'll tell you the story later. So number 2 says that a man pushes a car. A man pushes a car of mass that. The mass of the car is number 2. The mass of the car is 1,800 kilograms through a distance of 100 meters. The distance is 100 meters. Distance is 100 meters. With a force of 600 Newton. The force he applies is 600 Newton. He says we should calculate A, the work done. A, work done. A says work done. And B says the acceleration. So let's calculate work done first. In this case, the work done is going to be what? Force times distance. So that is 600 by distance moved, 100. That becomes 60,000 joules. That's the work done. Then he now says we should calculate the acceleration. B says calculate the acceleration. The acceleration of the car as a result of the force. So that's very simple. You remember that, you recall that force is equal to mass times acceleration. Now, what is the force that the guy applied? 600 Newton. So you say 600 Newton is equal to mass 1,800. Then the acceleration to produce is what? Is that okay? Then you divide both sides by 1,800. Here 1,800. This. Here 1, here 3. So the acceleration equal to 1 over 3, that's 0.33 meters per second. Per second squared. That's the unit of acceleration, don't forget. Unit of acceleration. Then number 3 question says, number 3 says, a 10 kilogram block, the mass of the block is 10 kilograms, is pushed 8 meters across a horizontal floor. You'll be writing your parameters, okay? Is pushed 8 meters, distance moved is what? 8 meters. 8 meters across a horizontal floor by a horizontal force. So the force is horizontal. Of 25 Newton. The force applied is horizontal and the magnitude is 25 Newton. The coefficient of kinetic friction, so mu sub k now, mu sub k is 0.3. Okay, it doesn't have a unit. Yes, it doesn't have a unit. And if you don't understand that, I have discussed something like this in dimension analysis, so you can see the link in the description for that. How much work is done in overcoming friction? How much work is done in overcoming friction? Okay? So we're looking for work done in overcoming friction. The work done in overcoming friction will be the frictional force times the distance. So that is the magnitude of the frictional force times the distance. That is the magnitude of work. This frictional force, this is the value of the frictional force, F sub F, okay? So if the frictional force is going to be the one, the value of this frictional force is the amount of force we need to just overcome friction. Is that clear? So for that body to move, it means we applied more force. Does that make sense? Since there is friction on the table or on the whatever platform is moving on, the magnitude of the force that overcame friction is just the magnitude of the frictional force itself. That is the force that just overcomes it. So the remaining motion is due to net force acting on it. That is, there are some extra forces, or there is extra force that was applied that is greater than even the frictional force itself. Because if you apply a force that is less than the frictional force, the body will not move. If the body moved, then you applied a force that was equal to the frictional force and greater than it. Exactly. All right, so let's do that. First, let's find the frictional force. Recall that frictional force is given by how do we know that? We write F sub r. Let's use F sub r, please. F sub r. That is, you remember that the coefficient of static friction is frictional force over the ratio of frictional force to normal reaction. Do you remember? The ratio of frictional force to normal reaction. So if that's the case, that's what we call coefficient of friction. So F sub r therefore becomes mu r, okay? And for a body that is on the horizontal ground, r is going to be equal to the weight of the body, which is equal to what? Mg. Does that make sense? Therefore, F sub r becomes mu, in which case here we are dealing with mu sub k. There are two types of mu. We have mu sub k and mu sub s. Mu sub k is coefficient of kinetic friction. Mu sub s is coefficient of static friction for body that is stationary. So mu, F sub r, which is mu r, and r is mg, that will be mu sub k times mg. Therefore, F sub r, in this case, will be, what is our mu sub k? 0.3. What's our mass? 10. What's our g? 9.8. All right, so 9.8, that's 98 times 3. 98 times 3. 294. So frictional force is equal to 29.4 Newton. 29.4 Newton. It means our body cannot move if frictional force is 29.4 Newton. So let me correct the question. Let's see. If the coefficient of friction is this much, okay, the body will not move because frictional force is already 29.4 Newton, and the force of that is applied. So if the body moved, let's probably reduce the coefficient of friction. No, 0.3 is fine. Let's use the mass. Let's reduce the mass. So let's do 5 kg. So if 5 kg is the mass, so here is 5. So half of that divided by 2. 14.7. Good. So 14.7 Newton. This is the frictional force. So what will be the work done in overcoming friction? Work done in overcoming friction is going to be the product of the frictional force times the distance the body moved. What's the frictional force? 14.7 times the distance d is 8. Okay, 8 meters. So that becomes times 8. That becomes 1176 joules. 1176 joules. Sorry. 117.6 joules. So this is going to be, this is the work done in overcoming friction. Then the second one now says, how much work is put into the acceleration of the body. Okay, that is how much force is now put into the acceleration of the body. Okay, so the first thing you have to know is that if 25 Newton of force is applied, then force applied is 25 Newton. Then the frictional force is 14.7 Newton. Then the net force that accelerated the body is going to be 25 plus minus this, okay, because frictional force will oppose it, right? So the F net will be 25 minus 14.7. Exactly. Yeah, 14.7. So 25 minus 14.7. That becomes 10.3. So F net is equal to 10.3 Newton. So this is the force that accelerated the body. So how much is now put into accelerating the body? Okay, that's it. So no, how much work is put into, not how much force. This is the force that accelerates the body. So work net that does the work is now going to be F net times the distance moved. So equal to 10.3 times the distance it moves is 8. So 10.3 times 8, that's 82.4 joules. This is how much is used to overcome friction. This is how much is put into accelerating the body. Now let's go to energy. Energy, let me pause the video. All right, so you really need to listen to this aspect, which is energy. So make sure you listen carefully and write notes, okay? So energy in itself is a complex term to define, okay? You ask any scientist now, they can't exactly tell you what specifically energy is. But so the simplified definition of energy is just the capacity to do work, or basically what you use to overcome work. Is that okay? What you use to overcome work, that is energy. So energy is capacity. We say it is the capacity to do work. Okay? So what we do is actually that we convert energy to useful work. Okay? So energy is usually converted to what? Useful work. That is why they have the same unit of measurement. Energy and work. Okay? They have the same unit of measurement. Energy is that capacity. Okay? While the work itself is the product of the force that you apply and the distance over which you are able to move the object or displace the object. All right, so energy appears in different forms, okay? Energy appears in different forms. First, we describe energy, we classify energy into two types. There are energy types that are renewable, now more like forms of energy, okay? There are forms of energy that are renewable. Classification of energy, we have the sources of energy. Let's start. There are sources of energy, okay? Sources of energy. Not types, please. What are the sources of energy? So we have the renewable sources of energy. I've covered this before, so maybe I'll link the video in the description. Renewable sources of energy and the non-renewable. Now, what are non-renewable? What are renewable sources of energy? There are energy sources that can be used again after the energy that they provide have been used up, have been harvested. So they can still give us energy for as long as possible. Okay, we can recycle the energy. We can get the energy again. The energy that we have used up in it, we can regenerate it. Okay. An example of such source is the primary source or principal source of energy in nature, which is what? The solar energy. Is that okay? Solar energy. Other examples include wind energy, which one again? Tidal energy, or the one we have on the ocean, right? Ocean energy, which one again? So that's primarily it. Those are the major renewable energy. But the non-renewable ones are the ones that after we have harvested the energy, we can no longer get that same energy back. We need a new source, a new type to get energy again. We cannot reuse that energy again. It cannot be given. We cannot get that energy back again. Is that clear? So keep in mind though that energy is not created. It is only transformed from one form to another. Is that clear? So now non-renewable sources of energy include this one now. There's also geothermal energy, okay? There is geothermal example energy. I just remember that. etc. But here we have every other form of energy, every other source of energy are usually non-renewable. For example, coal, non-renewable. We have biogas, non-renewable. Okay, we have fossil fuel. Fossil fuel is non-renewable. I've covered this before. Maybe I'll link the video in the description. So these guys are non-renewable source of energy. Petroleum, you were waiting for me to say that, yeah? Of course, petroleum is non-renewable. Now let's not deal with the forms of energy. Before we do calculation, I would just like us to cover these things. What are the forms of energy? The forms of energy. So I would like to talk about this one in specificity later, which is mechanical energy. Now, mechanical energy is divided into two. That's one we want to treat. That's the one we'll focus on. Okay. So, and the two are the kinetic energy, and potential energy. Then the potential energy are of different forms. Okay. Potential energy are of different forms. Okay. So, in this case, we just deal with mechanical potential energy. Now, we have another form of energy is elastic potential. So, there's elastic potential energy. There's elastic potential energy. There is gravitational, the one that is very important. Gravitational potential energy. So let me just put P for short. There is also electrostatic potential energy. We call it electric potential, right? Electrostatic potential energy. We call it electric potential that we use V. Okay, electrostatic potential energy, that's W. So most of this energy we use W for them, okay? But this one we use GPE to represent it. This one we simply use E, elastic potential energy. And I've covered many of these things. I've covered this one in gravitational force. So you should see my video on 30 days of 5 days physics. So we have covered this thing. But of course, I'm going to deal with it in more detail now. I'll try to do this too. So we have electrostatic potential energy. Those are the potential energy. And of course, we have different other forms, including light energy, sound energy. And light energy is just we are dealing with electromagnetic radiation. Well, keeping in mind that light is just one of the electromagnetic spectrum, okay? So of course we have sound energy. We have internal energy. We have thermal energy that we call heat energy. Thermal or heat energy. We also have the nuclear energy. We also have the chemical energy. We have the chemical energy and electric energy. Okay, there is now don't mistake this. This one is electrostatic potential energy. This one is electrical energy or electrical energy. Okay, so there is that. You see, there are many forms of energy. There is probably still one or two that I have not mentioned. So these are the forms of energy. Now, what do we need to now discuss? Most importantly, we have the mechanical energy. Very important. Let's discuss the potential energy first. Potential energy. Now, the potential energy that the body has is the energy that the body has by virtue of its position. Energy of a body by virtue, you must have heard me discuss this as by virtue of its position above the ground, okay, or above the reference point. By virtue of its position, all right? So potential energy is given by the formula. Since in this case we are dealing with its position above the ground, so we call that a height, right? A height. So if that's the case, remember that work done is force times distance. So in this case, force times distance x. In this case, work done will be potential energy. It has been converted to energy, right? Useful work. Energy is converted to useful work, or work done is now potential energy. So if that's the case, the force here is going to be the weight of the object itself, and the distance here is going to be the height above the ground. Is that clear? So if that be the case, then work done, weight rather, is equal to mg. Okay, mass and acceleration due to gravity. Remember, 10 times h. So this is the formula for potential energy. The formula for potential energy. How about kinetic energy now? Kinetic energy. Now listen, I'm going to deal with a case where we, deal with conservation of energy after now. So how about kinetic energy? We can derive the formula for kinetic energy from here also. Kinetic energy is the energy of a moving body. Energy of what? Of a body in motion. So we call it Ke for short. Ke is going to be what? Now you remember we can derive it from P. We can derive it from P. What that means is this. What we want to do is this. I'll derive it in another way, okay? But I can actually derive it from here. If a body is at a height above the ground, and I'm going to use this analogy again. If a body is above at a height above the ground, when the body begins to fall, it gains kinetic energy, right? When the body begins to move downward, it gains kinetic energy. Given that it's starting from a height at velocity of 0, that is, it was not moving before from this height, it means the initial velocity is 0. Then recall that v squared is equal to u squared plus 2gh. Do you remember? So if this is the case, then u is 0. So v squared is equal to what? 2gh. So if that is the case, then h can be equal to what? V squared over 2g. Is this clear? So from there we can derive a formula and expression for kinetic energy such that kinetic energy will be equal to potential energy, which was mgh. You recall that P was the one that gave us mgh. So by the time we slot h in, Ke becomes mg times h, which is now v squared over 2g, right? So g takes care of g, and then our kinetic energy becomes mv squared over 2, or you might see it fondly written as half mv squared. Exactly. That's how to derive it, but I could also derive it in another way. For example, look at this. Now, if I have something like this, recall that work done is what? Force times distance. Okay? And using that same formula, so this is for if the body is starting with u being 0. What if u was not 0? U was actually, u were to be rather. If u were not 0 and u were add a value, then it means that from that equation, from v squared equal to u squared plus 2as. Now let's use 2ax now. X or s, if distance is x or s, whichever one you're using. X now will be equal to what? V squared minus u squared divided by 2a. By the time you make x subject of formula, this one comes here. V squared minus u squared divided by 2a, and you get this. Okay? If I substitute this into our equation, then w becomes f times v squared minus u squared over 2a. Is this clear? And recall that f is ma. Therefore, w becomes ma times v squared minus u squared over 2a. A takes care of a, in which case we have w to be equal to m into bracket v squared minus u squared over 2. Okay, and for that reason, we have that our kinetic energy now, our work done has become kinetic energy already, equal to mv squared over 2 minus mv squared over mu squared over 2. Okay, so now what this is this. What this is telling you is this, that kinetic energy, this kinetic energy here is the change in kinetic energy, or think of it as kinetic energy gained. Do you understand? Change in kinetic energy, the kinetic energy gained from initial to the new. The difference is the kinetic energy that has been gained. So therefore, delta Ke is equal to m is common between v squared minus u squared over 2. So that is that. Of course, so that is the formula for kinetic energy. Now let's solve some questions. All right, so now let's solve the following 3 questions. All right, an object of mass 100 grams, so using heuristic method, write your parameters. Number 1, mass is 100 grams. So which is how many kilograms? Divide this by, convert it to kilograms by dividing this by 1000. That becomes 0.1 kg. Okay? then projected vertically upwards from the ground level has a velocity this. So the velocity is 20 meters per second at a height of 10 meters. At a height 10 meters. Okay? Calculate its initial kinetic energy at the ground level. Calculate the initial, so let's call that one KE1, okay? KE1 at H equals 0, okay? At ground level. So what we want to do is this. You know that this is basically, we said that change in kinetic energy is equal to half mv squared minus half mu squared, right? So now seeing this, what we want to find is u first. Let's find the value of u. When we get the value of u, then we can know, okay, it's just this that we're looking for, this. This is what we're looking for because initial kinetic energy is what it says. So what do? You say the height is 10 meters. So recall that v squared is equal to u squared. The body is going up, right? Since the body is going up, so it will be minus, since it is projected vertically upwards, minus 2gh. So if that's the case, then we know that u will equal to this plus this. So v squared plus 2gh equals u squared. So u squared is equal to, what is v? That's 20 squared plus 2 times g, which is 10. If we are neglecting a resistance, 10 times h. H is 10, okay? So we have u squared equals 20 squared, that's 400, plus 100 times 2, 200. So u squared equals 600. Square, take root of both sides, so that u becomes the square root of 600. That will be 24 point something. Square root of 600, 25 is 65. That will be 24.49. Let's just say 24.5. 24.5. Approximately 24.5 meters per second. That's the u. So that's the, okay, it says to calculate the initial kinetic energy. So initial kinetic energy is half mu squared. Because by this we're able to get that the body was moving with 24.5 meters per second initially. So initial KE therefore becomes 1 over 2 times mass of the body 0.1 times u, which is 25, this squared, that is 600 squared. U squared is 600, right? U squared was 600. So we'll just use 600 here. I don't know if you understand me. If I square this, it will give me very close to 600, not exactly 600. But in fact, we know that u squared is actually 600 from here. U squared is equal to this plus that's 600. So we just apply, we just use this here. Exactly. So here 1, here 300. So that KE, initial KE becomes 0.1 times this, that's 30 joules. So that's the answer to that question. Then the next question says that a hammer with 1.5 kg head. Okay, a hammer with that's hammer head, okay. Let's clean that part. A hammer with 1.5 kg head. Mass of the hammer, number 2, is 1.5 kg. Is used to drive a nail into a wooden board. If the hammer head is moving at 4 meters per second, so the hammer head is moving with a velocity of 4 meters per second. When it strikes the nail, okay, and the nail moves 15 meters, it produces motion distance x is what? 15 millimeters. So we convert this to meters. When you are converting from millimeter to meter, you divide by 1000. That will be 1, 2, 3. That will be equal to 0.015. Because this is 100. 1, 2. 0.015 meters. Into the board. Calculate the average force the hammer exerts on the nail. Okay, so you have to find the force the hammer exerts on the nail. Now already you know that as the hammer is hitting, the hammer is using kinetic energy, right? The hammer has kinetic energy. So the kinetic energy of the hammer, kinetic energy of the hammer head is going to be equal to the work done on the nail. Is that okay? Work done on nail. So kinetic energy of the hammer is going to be equal to half mv squared equal to the work done on the nail will be the force times the distance it moves. So that's why we have to calculate the force. Exactly. So this becomes half. Do you understand this thing I said? That the kinetic energy of the hammer head is equal to the energy of the nail, which is equal to work done on the nail. So half mv squared, which is 1.5 times v squared, that's 4 squared, that's 16. Yeah, 4 squared, let's write it that way. Equal to the force on the nail times the distance the nail moves, 0.015. So by the time you do this, you get half here, half of this 4 squared is 8, right? 15 times 8, that's 120. Because 5 times 3, 5 times this, 40 times 3. So the one that's 120. 120 equal to 0.015 F. Divide both sides by 0.015. By 0.015. So F will be equal to 1, 2, 1, 2. You don't even need calculator, honestly. 1, 2, 3. We move from here. 1, 2, 3. So we have 120,000 divided by 15. Already we know that 15 in 120 is 8. Sorry. 8 times 15 is 120. So this is supposed to be 12 because it's 1.5. It's 12. So 12,000 divided by 15. So we have 120 is 800. The answer is 800 Newton. Exactly, 800 Newton. All right, the next one. The next one says that an object is moving with a velocity of that. An object, number 3, is moving with velocity of 5 meters per second. At what height must a similar body, okay, they will have the same mass, right? Mass of 1 will be equal to mass of 2. So m is m. At what height will that body be situated to have a potential energy equal to the value of the kinetic energy of the moving body? Okay, very simple. You just say that at what point will PE be equal to KE? At what height? So what will be the height? That's what we're looking for. So recall that P is mgh equal to kinetic energy is half mv squared. So the masses are the same, so this takes care of this, right? Since the masses are the same, so m can cancel m if you divide both sides by m. And of course, it's the h we are looking for, right? So h divided both sides by g, you have 1 over 2v squared over g. Exactly. So h therefore becomes 1 over 2 times, what is v? 5 squared, that's 25 over g. If g is taken to be 10, let's use 9.8 since you have calculator. So 25 divided by so this becomes 1. The h is 1.2755. So that'll be like 1.28, approximately 1.28 meters. So this is the height at which the kinetic energy will be equal to the potential energy. Now, one more thing we have to talk about under energy is conservation of energy. Before we talk about power, power is the last thing here. Before we talk about conservation of energy, before we talk about conservation of energy, before we talk about power rather, you have to know about conservation of energy. Now, conservation of energy is what we have seen here actually, of energy, okay? Now that's just how that, the principle states that energy is transformed, energy is not created, is the same as the first law of thermodynamics. which is saying that energy is not created nor destroyed. Energy is only transformed from one form to another. Now you should watch out for my video on thermochemistry. I'm going to discuss all these things in details. So if you find energy in this room, so if we have in this room 300 kilojoules of energy, and by the time we leave and come back, we meet 500 kilojoules of energy. Now, you won't say that 200 kilojoules have been added. What you will say is that some form of energy, something has happened that has released more energy to add to that 300 kilojoules of energy. Is that okay? So energy is not created nor destroyed, but transformed from one form to another. So total energy is always what? Conserved. Total energy is conserved. Okay? No energy is created. No energy is created and no energy is destroyed nor destroyed. Okay? It has only been converted, it's only been converted, but converted from one form to another. So that is what the principle of total conservation of energy is about. So what that means is this. Let me quickly show you an analogy. So if I have a body like this, so there's a body on this hill, there's a cliff, for example, and this is the horizontal ground. Now the height of this cliff is h. This body has mass m. The height of this cliff, let's call it h. So at this point, this body has only potential energy. Okay? Now if this body rolls off to the ground, let's try to be consistent with the size. Okay, rolls up to the ground. Now something will happen. Now this height here at this point is less than the height here, right? Less than this height here, isn't it? So what has happened is that potential energy has reduced. So from this point here to this point here, potential energy has reduced. It has dropped. From that point here downward again, potential energy has dropped. But that energy, that dropping in energy, has it gone somewhere? Has the energy disappeared or something? No. The energy has only been transformed to another new form. So from here to here, some conversion has gone to what? Kinetic energy. But of course, we know because it's still at a height above the ground, even at this place, it still has what? Potential energy. But what will happen is that the total energy here is going to be what? Potential plus kinetic. Then you might be forced to think that potential and kinetic, if you add them together, it will be more than this. No. If this body started with 200 joules, for example, by the time it gets down here, by the time it gets here, some potential energy, the total energy here is potential because the body is not moving at all. So by the time it gets somewhere here, the total energy may have dropped to about 180 joules. So where did the remaining 20 joules go? The remaining 20 has become kinetic. The energy is used in moving. That's why the velocity will not have increased so much here. Because that's the actual, the only quantity that affects the value of the kinetic energy there. The value of the energy. The velocity rather. The velocity. So by the time it gets down here, maybe the potential energy may have become 150 joules. It means only that the remaining 50 has been converted to what? Kinetic. Is kinetic here. These have become potential. What you notice is that midway down the distance, this has become 100 joules, and this one would have dropped has also become what? 100 joules. Do you understand? It does not mean that it is at midway that this happens, okay? Because this depends on the speed at which the body is moving. But I'm assuming for you to understand that midway down through the fall, this potential energy is now half of the initial energy. The remaining half is going to be the kinetic energy. And it is such that just before this body comes to rest on the ground here, potential energy becomes zero because the height here is zero. Then total energy will be what? Kinetic. All energy will be kinetic. And at that point, the total kinetic will be what? 200 joules. So do you see that the energy only kept undergoing transformation, but nothing was really lost. In real life, some energy will be lost, okay? In real life, some energy will be lost, maybe due to collision or something. Different things might cause energy to be lost, but in an isolated system, we assume that no energy is lost, all the energy is conserved. Now, let's go to power. So what is power? Power is simply the time rate of work done. Power is simply what? The time rate of work done. Time rate of work done. That is the rate at which work is done. Right? What does that mean? That is work done per unit of time. That's the meaning of power. Work done per unit of time. So it's more about speed, in fact. So if I say I have more power than you, it means I can do more work in less time. That's the meaning. I can do more work in less time, or I can do the same work in less time, or I can do Is it I say I can do more work in less time, or more work in the same time? Yes, there are three definitions. If I say I have more power than you, means I can do more work in less time, or do more work in the same time, or do the same work in less time. All of those still means that I have more power than you. That's the meaning. Is that clear? All right, so that is power. So this is basically it. Okay, so we can now use different transformations. Work done, we got it to be force times distance over t. This is the first equation. Another equation could give us force times distance s cos theta over t. That's another equation. We could also use energy, okay? Power will be mgh over t, another equation. And power could also be our half mv squared over t. So more like v squared over 2t, that is, you understand, that is also another formula. So what this formula is saying is that it's just about just the different transformation of energy that can take place, okay? Then include time, take their time rate, then you get your answer. So that's how to apply, that's pretty much how to solve it. Now let me solve maybe one or two questions on power, and we'll call it a day. All right, so I'm going to be solving just two questions. It says, a man weighing 800 Newton climbs up a flight of stairs. So the weight of the man is 800 Newton, and he climbs up a flight of stairs of height 15 meters in time 12.5 seconds. What is the man's average power? So what is formula for power in this case? Power is going to be force times height, right? That is force times height divided by, this W is no work, it's weight, okay? That will be force times height divided by time. So that will be weight times height over t. So that becomes, what's the weight? 800 times the height, 15 divided by 12.5. And the power, I'm very sorry I didn't tell you, the unit of power is watt. Okay, I didn't mention it here. Unit of power, SI unit of power is watt, okay? Now, watt is also, there's another unit which is called horsepower. So one horsepower. One horsepower is equal to 746 watts, or you must have seen it in your textbook as 750 watts, approximately that. So one horsepower is 746 watts. By the time we use our calculator, we'll find that 120 divided by 120, okay. 800 times 15, 12,000 divided by 12.5, that's 960. So the power is 960 watts. W for watt. Is that okay? Or 0.96 kilowatts if you were told to convert. Then question 2 says that the man uses a horizontal force. So there is a question. Horizontal force of 500 Newton. See how simple the questions are. So reach out to me on this number to send you questions. There are many questions that I have on this, okay? And of course, both A level and O level, okay? So 500 that to push a crate up a ramp. So this is a ramp. I've drawn this for you separately also. So there's a ramp here. We incline our guy. So the guy is pushing a crate. All right, it's pushing a crate up the incline. Okay. So he's pushing this crate. He's pushing it up. This guy. He's pushing it up. And this thing is inclined at an angle theta. So that's what we're just doing. Okay. And remember, it is the, so maybe he's pushing it into a lorry. So remember that it's this horizontal component that we're concerned about, right? Which is F cos theta. So the ramp is 12 meters long and 12 meters long, and that is 60 degrees above the horizontal. 60 degrees above the horizontal. Okay. So the distance moved is here, right? Along this plane. So if we bring our guy, at the end of the day, it's still F cos theta, okay? So it becomes distance moved is 12 meters, or x. You see, you can use d or s or x for distance, okay? So the power, therefore, and the work done, that's what I have to calculate. Work done of what? Force times cos theta times distance. So F is 500 times cos theta. What is the theta there? 60 degrees. Times what is S? 12. So that becomes half. 1/2 times 500 times 12. Here, let's use 6 here. Here's 6. So 500 times 6, 30, 0. So the answer is 3000 joules of work. So that is 3 kilojoules. 3 kilojoules. How did I get 3 kilojoules? You know that 1,000 means kilo, or kilo means 1,000. So 3,000 joules means 3 kilojoules. Is that clear? Alright, so then the B part says, I'll bring the B part here. The B part says that if the man takes 10 seconds to push the crate up the ramp, what is the power output? Power equal to F cos theta, that formula. F cos theta times distance over T. I've got F cos theta to be 3,000, right? Over T, that's 10. So answer is what? 300 watts. Sorry, this is power now. 300 watts. Okay, in watts and in horsepower. So in horsepower, remember that 1 horsepower is equal to 746 watts. Therefore, 300 watts will be equal to, therefore, how many horsepower rather will be 300 watts? Okay, so you cross multiply, and it becomes x equal to 300 divided by 746. 300 divided by 746. 0.402 watts, horsepower, sorry. Horsepower is abbreviated HP. Is that clear? Alright, so that's it for this video. Another thing you might be tested on is what's the efficiency of something, okay? Efficiency is basically equal to the power efficiency, let's call it E, is equal to the power output over power input times 100. Exactly, so that's how you get that. So that will be it for this video. Do well to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. God bless you. And share this video with your friends as well.